Okay, shall we start? Hi, everybody. So, last time we talked about clustering, right? Last week we talked about clustering. So the idea was, what we see in our data, this pattern that the data samples are clustered into sets of samples, like subsets, subgroups, and then want to just cluster it, right? And then we started with the intuitive idea, just doing the k-means clustering. It made sense, and then we tried to somehow make it a bit more concrete. So this was what we did in our last session. So last lecture, it was about just deriving why k-means clustering is actually working fine. But all of this can be represented in a much more generic framework, which is called distribution learning, density estimation. And then this is pretty much the general recipe for everything you do in machine learning, at least if you look at everything statistically. So how many of you have heard of this, like we are doing classification with cross entropy, and we are basically doing maximum likelihood. Have you heard of this? That we are just doing maximum likelihood learning. And as you're going to see today, and a part of it remains for Thursday, this is actually a very general solution for any learning problem, as long as you can interpret it properly into density learning. So today I'm going to explain this. I start from basics to just recap a bit of probability theory, and then we get into maximum likelihood. So essentially, this is the problem that we want to learn. We want to talk about distribution learning, or basically density estimation. You see that they are the same thing. And then first of all, we just get a bit of recap on probability theory. I talk a bit about probabilistic modeling of data, so you get the idea what is the key problem here. And then we're going to get into maximum likelihood approach. This is the general recipe. Pretty much anything you do, at least in a normal sense of machine learning, you're basically one way or another doing maximum likelihood. And many times you don't know that you are doing maximum likelihood, but basically you are doing maximum likelihood. Cross entropy, if you compute, you're doing maximum likelihood. If you are computing MSE in regression, you basically do a maximum likelihood and things like that. So this is, as I said, say the mother of all these things that we study in this lecture somehow. And then we are going to get back to the clustering problem, which we have learned up to this point. So we talked about clustering problem. We see that we basically have done a sort of maximum likelihood with very naive basic model. And then we can actually give a bit of extension beyond that. Then on Thursday, I'm going to give you a bit of more discussion on Gaussian mixture model, which is a more generic model, and then how we can do maximum likelihood with that one. And then you're going to see that, for example, this makes sense, at least theoretically, in terms of data generation. If you want to generate a new image, it's basically the same problem, but you need to go under a huge computation task, which is not covered in this course, but in other courses. But the key framework is just explained in the shadow of this density learning. So let's just start with the original problem. So let me let's get back to the clustering problem that we had. So one thing that might be interesting for people who are doing clustering is the problem of outlier selection. Like, you want to understand if there is an outlier inside your data or not. So I think initially I just motivated the whole story with that particular example of the number of transactions and the amount of transaction. We have two different clusters of data, right? All the samples are either like so many transactions with each of them being very small, or a few transactions very large, right? But they're not like, there are few points outside these clusters, right? So it might be that your data is somehow focused on multiple clusters, and there's one guy which is somehow far away from all the clusters, right? And this guy could be your outlier, right? But why this is outlier? Well, this is coming from some alternative thing. I mean, I do understand that this might make sense in terms of clustering to you intuitively, but even if it makes sense to you, you're actually thinking with a kind of statistical way of thinking to this data. So what you're thinking about is basically you think about this data coming from a bunch of distributions, right? You might say when this is in this cluster, it should be around that. Being around something, it means like you are randomly distributed, but you are not supposed to go far away, right? But when something is outside all of them, this means that it's outside the normal distribution that you expect, okay? Let's look at this particular example. Let's say I have this data, so I am going in some, I don't know, casino or something, and I start playing with some machine, and this xn is whether I win or lose, right? Each time that I play, I win or I lose. And then maybe I collect n different samples, right? Now, I collect, like this is the data that I'm collecting, so I go there, I play 10 times. First day I win, I lose, I lose, I win, and so on. And out of this one, if you look at this guy, so now you have this question. You want to know whether, based on this observation that I have done up to this point, is such an observation in the next 3 days a kind of typical thing to happen or not? Like, I have gone and played a couple of times, and I have seen these samples, these outputs. Now, I claim to you that, okay, it's true, like any loser, like it's true, I have lost a lot, but in the next 3 days, I'm going to win every day, right? Now, you are not going to buy my words, right? How do you do that, right? Why you don't believe that I'm going to win every day from now on? Because you look at these samples, right? You would say if you wanted to win, you could have won at least 3 days in a row before, right? You have not done this, right? You have just played a lot, but every time you mostly lost, right? Maybe you won out of a sudden, but mostly you lose, right? So the main thing happening inside your brain is that you look at these numbers and somehow you think of my outcome as a random process, right? I can win or I can lose, right? But the chance of winning is much smaller than losing, right? And somehow in your brain you would say, first day winning, maybe it has, I don't know, 3 out of 10, 30% chance. But winning the first day and second day is like 30% times 30%. No, it's going to be smaller, right? It's 9%, right? And then the third day winning is like 30% times 30%, then 30%, right? Is 0.027, right? Yeah. So it's very small, correct? So it means that there is a very small chance that I'm going to win on that day, right? This happens. And if I claim that even I win more, you give up on my claim more and more, because the more I claim I win, the lower it could get the chance, right? So what basically you are doing, you're thinking of the data to be a sort of random process, right? So the data that I have collected in these n days, you're thinking of this to be a sort of random process, samples coming from a random process. I can win, I can lose, there are chances there. And then you consider a sort of model. That model is trying to explain these chances, right? What is the normal chance of winning? Based on what you have seen in my last 10 days, you would say it's 30%, 0.3, right? Everybody's cool? You see what I'm talking? Yeah? Okay, so this is the kind of way that you think about the data. So the model that you are doing, you're basically making this pattern in your brain, that in your mind, that, well, a normal pattern is that you lose most of the time, right? 70% of the time, and you win a few times, right? And out of that, you are somehow building a sort of learning algorithm in your mind, right? You see the data, you know the pattern, there is a pattern, there is chances for winning and losing. And now, out of the data that I see, I want to just compute that chances, right? So it's still a learning problem. You have data, you have pattern. The pattern is this, the way that you describe a normal outcome from this process, right? And the learning algorithm is basically the the mechanism that starting from the data, you're going to understand what is the normal situation, right? What is the normal output of this random process, right? Everybody's cool, right? So it's not a weird thing. You do it all the time, right? Every day. And now what we want to do, we want to somehow concretely formulate it. And then when we formulate it, we want to find out what is that right learning algorithm. This is what we call it maximum likelihood. So let's just start with this stochastic viewpoint on the data. What I do, I assume that every single sample that is coming from inside my data set is actually coming from a random process, right? Process of winning or losing, right? And it has some chances. Now, every time I go and play, one outcome, one sample of this random process is happening, right? And I'm going to write down that sample. So these samples that I have inside my data set, these are samples of that random process. You can extend this idea to anything. We're going to later do it next session to more serious data. For example, if there is an image, right? One image. Maybe you think about image of a cat, right? Now, if I tell you here, without showing you, there is image of a cat, there are lots of cats coming to your mind, right? Correct? So this is a random process. I have not shown you the image of the cat yet, right? But once I show you the image, now you see the cat, right? This is one sample. I can again hide it, and I show one other cat, right? That is another sample. And I can keep on doing this for all the images that I have, right? So every single image of a cat here is a sample from the process of a random cat-generated image of a cat, right? And so on. Yeah? For text, the same thing. For audio, the same thing, and so on, right? So this is the data that you have. And now the thing is that if this guy is a random process, if this is coming from a random process, that process has a distribution, right? Now, I want to know what is that distribution. And here is where the model comes from, in. So I'm going to assume that this data is distributed with one specific distribution, right? Now, how do I know that? Well, maybe I don't know it. Maybe I'm just modeling that data, right? I feel like this data is Gaussian. I feel like this data is Laplace. I feel like this data is some exponential distribution, right? So it might be my feeling. There might be some reasoning behind it. Or it might be that the distribution that I am thinking of, or I'm considering, assuming, that is very general. This is capable of describing many, many, many distributions, right? And this is what we do in Gaussian mixture model. Like, we build a distribution which is capable of doing many things, right? But right now, you're going to assume that this guy is coming from a random process. This process has a specific distribution. And then the whole process that we want, we do is that we'll look at this data set D that we have, and we try to describe that distribution. We try to find out the parameters inside that distribution, exactly what they are, right? So this is the problem of density learning. So data are samples coming from a random process. Maybe this is really a random process, like the example I told you. Maybe this is not a random process. You're just modeling it as a random process. Like, for instance, if I get a coin and I just flip it, it goes up, comes down. Well, if you do know all the dynamics of this environment, you can write down the dynamic equation, right? And you can explain exactly on which face it's going to land, right? But you're not going to do it. It's going to be a nightmare, right? So you're going to model it as a random process. This is another thing, right? It might be the case, but at the end of the day, I have a bunch of samples from what I call it random process. And now I try to describe its distribution in some form, and then I try to start from the data, build one learning algorithm to learn what that distribution is. Okay? So now, before I start working with this guy, I just want to recap a bit of notation from and some notions from probability theory. I do know many of them are more than clear for all of you, but just to be sure that we are all on the same page. Okay? I try to be quick, but if you find anything like you forget that, you want a deeper recap, just let me know. Okay? So first of all, if I have a discrete random variable, say x is a discrete random variable, it means that it has one specific number of outcomes, right? A1, A2 to AI, this could be, these are the possible outcomes, right? a binary coin. It could be head or tail, right? 0, 1, for instance, right? So this is a discrete random variable, and then I can show such a notation. X is distributed by px. What is px? It's a probability mass function, right? So it means that if I put x to be ai, it's going to be the probability of that particular outcome, right? P of 0 is the probability of seeing head. P of 1 is the probability of seeing tail, right? Now, the key feature of this probability is that this number, what is the range for this number? 0 to 1, right? So this number is definitely something between 0 and 1. And there is one other property. If I add up the probability of all outcomes, it's going to be 1, right? So this is the next property. So px is this function, which is operating on x and giving me one number between 0 and 1, is a probability distribution if this thing happens, right? So any function that you put there has this property. This is a probability distribution. This is what, indeed, this px is a probability mass function, because it's giving you the probability of every single mass, every single outcome that you have, right? The value of the probability for every single outcome that you have, you get it with a probability mass function. But we usually call it distribution because we want to uniform it across the with the other case, which is the continuous, right? So the other thing, okay, one example, yeah, Bernoulli distribution. I just give you this particular notation because I'm going to use it next. So I have x. X is being 0 or 1. And then when I write it down Bernoulli theta, I simply mean that this is a random process, and the probability of x being 1 is theta. Obviously, probability of x being 0 should be 1 minus theta, right? Everybody's cool? So if I tell you I have a Bernoulli distribution with parameter theta, everything is obvious to you, right? So the only parameter you need to know to write down this probability distribution is the value of theta. Everybody's cool, right? So this is a discrete random variable, and yeah, nothing specific about that. Now, the next thing is continuous random variable. Well, a random variable could be continuous. It could be any real number, right? And in that case, you cannot define a probability mass anymore. You need to define density, right? So if you want to define density, what you say I have this particular function px. This is now the density function. And what I want, what it computes for me, if I integrate it from a to b, is going to tell me what is the chance of x being between a and b, right? Everybody's cool, right? So this is the probability density function. Again, this guy should be, can it be negative? No, it should be positive. But can it be more than 1? It should be more, it could be more than 1, right? At one single point, it could be more than 1, right? Like a Gaussian distribution, for example, right? Because it's not giving you probability, it's giving you density, right? When you integrate it, you get probability, right? And it's probability which should be between 0 and 1. Density does not need to be between 0 and 1. So this is the key difference. It's positive, but, or non-negative, but it can be more than 1. But again, the key point is that if you integrate it from minus infinity to plus infinity, it's going to add up to 1. Because what is the chance of your random number being between minus infinity and plus infinity? Well, definitely it's 1, right? Whatever the distribution is. Everybody's cool, right? Again, this is probability density function, so we are not working with the masses. We are working with the density, but it's no problem. We still call it distribution, right? So if I show you this notation, x distributed by px, well, depending on x is discrete or continuous, you do know whether I'm talking about density or mass function, right? Cool. So now, one example of continuous random variable. Famous example is the Gaussian distribution, right? And this Gaussian distribution is parameterized with these two parameters. Mu is the mean value, and the variance is sigma squared. So how can I describe this random variable? Analytically, I can write down the density function, right? This guy. And this expression, first of all, this is an exponential function. This is definitely non-negative. Well, it could be more than 1, right? depending on sigma value, right? If sigma is very, very small, then this term in the denominator is small, right? And then this whole fraction is more than 1. Then if I set x exactly mu, then the exponent is 0. So it's going to be something more than 1 times 1. This could be more than 1, right? But the key point is that if you integrate it all over the axis, this is going to be 1, right? Again, if I want to describe this normal distribution, I need to only know the variance and mean value, right? If I give you these 2 parameters, you are able to write down the density function, right? Everybody's cool? Questions? No question? Now, this is the classic Bell-like distribution for Gaussian, right? And again, you can treat density somehow proportional to the chances, right? So when the density is high, for example, if you integrate the whole density function within this interval. So this is the center, the mean value mu. This is where exactly the density is largest value. And then within an interval variance around it, so from minus sigma to plus sigma around this mu, you have almost 70% of the chances of your output happening, right? And then here in this other part, you get less chances, right? And then when you consider, for example, 3 sigma, so this is the mean value, you go 3 sigma back and 3 sigma forward. Within this interval, more than 99% of the cases happen, right? This is why if you have a random generator, a Gaussian random generator, and you run it all the time, you can roughly see, I mean, it's pretty much impossible that you see anything outside this interval, right? Most of the samples you see on your computer are within this scope. Mean value, somewhere between 3 standard deviation from that, right? I mean, if you run it for, I don't know, 1,000, 10,000 times, then you start to see singular samples outside, right? But rather than that, most of the time you see everything here, right? Around the mean. Everybody's cool, right? Great. So now, one other thing regarding the random processes. So when I have x and y and I call them independent, this simply means that the joint distribution of them, I can write it down in terms of the multiplication of those 2 distributions, right? This sample is happening independent of this one, right? What is the chances? What is the chance of both of them happening together? Well, the chance of this one happening times the chance of the other one happening, right? So this is independent random variable, and we have IID sequence. IID sequence is a sequence of independent random variables which are coming from the same distribution, right? So if you have x1 to xn, and all of them are generated with the same distribution and independently, then this is an IID sequence. Example of IID sequence, you have a coin, you just flip it n times, right? N different samples, they are all independent, right? And they are all distributed the same, Bernoulli, right? Everybody's cool, yeah? Okay. Now let's consider this particular example. So I have one Bernoulli random variable, BR theta. So theta is the probability of 1 happening. And then I have just sampled this distribution 5 times independently. Now, the way that you might think about it is that I have this BR theta, Bernoulli theta. This is one machine. And I have pressed the button 5 times, right? And each time I see one number. It is either 0 or 1, right? But there are samples coming from this machine, right? And theta is giving me the probability of 1 happening. So I have seen these 5 different values. Now, if I want to know what is the joint distribution of these 5 different samples happening together, how can I compute that? What it would be? What is the chance of seeing this output after 5 times pressing that button? Multiplying them, right? So I'm going to write it down, probability of x1 to x5 being these guys. P of 1 times P of 1, P of 0, P of 1, P of 0, right? So I have 3 zeros, all of them, 2 zeros, both of them happening 1 minus theta. 3 ones, all of them happening with probability of theta. This is the chance of me seeing that output, right? After pressing 5 times. Everybody's cool? Questions? Yep.
So in this case, would you say that the distribution is a Bernoulli distribution?
The distribution is a Bernoulli distribution with parameter theta, right? No. Questions? Okay, cool. So same thing, you can think of Gaussian distribution. Say I have 0 mean unit variance Gaussian distribution. I have 3 independent random variables, so I have 0.3 randomly sample this distribution. Again, I have a Gaussian number generator. I press the button 3 times. I see these 3 numbers, 0.3 minus 1.5, minus 0.1. These are the three samples that I have. And then I want to compute the joint density of them, right? The joint distribution. Well, I can draw the Gaussian distribution. This is 0 with variance 1. And then I look at this guy, and then I go and sample it exactly at the 3 points that I have, right? And I multiply those points together, right? If you do that, this is going to be basically e to power minus every single of them squared, right? And then you have this term to power 3, right? So no magic, just I get the same distribution. I multiply it multiple times at the different points, right? So everybody's cool, right? Okay, one last thing, expectation of one function, right? So if you have a function of a random variable, fx, right? And I have this guy, I want to know what is the expectation of it. How can I compute this expectation? Well, if this is a discrete random variable, I'm going to compute f at every possible outcome. Say x is a binary random variable. I compute f at 0. I compute f at 1, right? I multiply f at 0 with probability of 0. I multiply f at 1 with probability 1. I add them up, right? This is going to be expectation when x is discrete. I can do the same thing, but this time instead of summing out, I need to integrate, right? And this is going to be the expectation of a continuous random variable, right? So the definition here is not important. The key or important thing about it is the intuitive description of this expectation. So what does it mean in practice? In practice, it means your average of that f, if you just try this infinite number of times with an IID sequence. So say I have x1 till xn being IID. It means that I got that machine, I press that button n times, right? I got n different samples. And I compute my function f at every single of those samples, right? And I average this output. If I average this guy, when n is large enough, so if I have enough number of samples, then this average is going to be the expectation, right? So the expectation is eventually the asymptotic version of the average I'm computing, right? Everybody's clear? So this is what we call it law of large number, right? If n is large enough, then this thing is going to happen, right? And now we can actually try it, for instance, for Bernoulli random variable. Let's look at this one. First of all, let's compute the expectation of x when it's Bernoulli. What is the expectation of x if x is Bernoulli? 0 times 1 minus theta plus 1 times theta is going to be theta, right? The expectation of x is theta, but this expression can be understood again by the intuitive illustration, right? So what I could say, I could say I have n different independent Bernoulli samples, right? Now, if I just generate, say, 100 samples, all of them are coming from, say, a Bernoulli with probability half. So if I press one machine, Bernoulli machine with probability half, theta equal by 0.5. If I press that 100 times, how many times you see 1? Roughly 50 times, right? How many times you see 0? 50 times. If you add them up, you divide it by 100. What it would be? 0.5, right? If it is theta in general, theta fraction of times it's 1. 1 minus theta fraction of times is 0. If you add them up divided by the number of samples you get, you roughly get theta, right? It's true if n is 100, 1,000, 10,000. This could be not exactly half. It could be 0.49 or 0.51. But as you increase the number of samples, this is getting closer and closer to half, right? And eventually at very, very large n, it's half, right? Everybody's cool? So you can interpret this expectation always like this. This is important for the rest of the course because whenever I show expectation of something, I want you to think in terms of averaging, right? So you would say if I have enough samples, I can approximately compute this, right? If I don't tell you exactly what is the distribution of x, I only tell you I want to know what is expectation of x. And I give you so many samples, it's okay. You're going to add them up divided by the number of samples you have. You roughly get the idea what is that, right? Everybody's cool, right? Good. So next thing, another example, Gaussian distribution. So if you have a Gaussian distribution, you can go ahead at home and do calculate these integrals. I'm pretty sure you have done it before in your courses. So the expectation of x is the mu parameter, right? The mu is the mean value, is the average value. That is the expectation of x. If you compute x minus mu, so you first centralize x, right? You just subtract x from its mean, which means you put it at the center, right? And then you square it and you take the expectation. This is what we call it variance. And that is going to be sigma squared, right? Now, again, you can do this by analytic calculation, but this intuitively means that if you have so many Gaussian samples, if you get simply those samples, you add them up, divided by the number of samples you have, you get the mu value roughly, right? That is approximately mu. Now, if you get that mu, you subtract every single sample from that mu first, you square it, whatever you get, you add it up over the whole data set, you divide it by the number of samples you have, you're going to end up roughly with sigma squared. Everybody's cool? Questions? Now, some of you might have had some course in statistics, and you do know that. You can just ignore what I'm saying right now, but for those who have heard of this before, you have an unbiased, this guy is a biased estimator. If you want to have unbiased, you need n minus 1. Those of you who had some course in statistics might think of that right now, but that is not important because when n is large enough, 1 over n and 1 over n minus 1 do not differ, right? They're the same thing, right? So you don't need to complicate things. We're going to get to that point to talk about bias and variance later on. Everybody's cool? Questions? No question. Okay, great. So if you have, I talked only about random variables, but you can think of random objects. So essentially, you can have x's to be vectors, matrices, larger objects like multidimensional tensor, and all of them are the same thing. If you want, you can think of them as a random object, right? One matrix is generated randomly. What you see is a sample. You could have lots of that, right? And when you talk about the distribution of those objects, like a vector or a matrix or whatever, you're talking about the joint distribution of the entries, right? But you don't need to complicate things right now. If we need to complicate things, I'm going to let you know. Okay? Questions? Everybody's clear? Okay. So if you're clear, then let's get back to our problem that we started to discuss. So we talked about learning the distribution of one random process. This is what we wanted to do. So what does that mean? This means that we need to model one random process that we are seeing the samples from. We need to model it as one specific random process. Then we need to be able to describe that process by a distribution, like a density function or a mass function. And we need to try to find out how we can perfectly match that distribution on the data that we have, right? This is what we want to do. Now, when you look at the data, this is the point that I told you. There are many ways that you can model a distribution for that. The first one is that the data is extremely simple. For example, it's a binary data, right? So the output is either 0 or 1. And then you would say, okay, what could be the distribution of one binary, if not Bernoulli, right? This is one way of thinking about it. Or you have real valued samples, but you have so many of them. Like you go out and check the height of every single person. So you collect lots of data. Well, you cannot say that you have collected the height of everybody on the planet. And even if you do it for everybody on the planet, you have not collected the guys before you and the guys coming after your time, right? So you cannot say this, right? You don't have access to all possible outcomes, right? But what you can do, you can get those samples. There are a lot. You can plot a histogram. And maybe it looks like a Gaussian histogram, right? Like there is one place where most of things are concentrated. And then when you get out of that, the chances are dropping symmetrically down, right? Maybe this is the case. And then you would say, OK, I assume that data distribution is Gaussian. This is what way that you can do. Or maybe your data is extremely complex, like images, right? Now, how can I think of that? Then here is the key problem. This is what you do in generative AI. So you need to think about one distribution, which is quite generic. It means that this distribution is able to describe any other distribution, right? So if this distribution, I set this parameter to that, this is Gaussian, but if I change that one, now it's exponential. If I change that one, it's going to be something else, and so on, right? So you have one expression, one kind of density, which is very generic, right? This is what we try to just mildly do next session with the Gaussian mixture model, right? So there are a bunch of ways that you might see the pattern inside your data, or you put an assumption on your distribution. But whatever that is, it's not important right now. The key point is, at the end of the day, you're going to think of one distribution, right? And that distribution has a bunch of parameters, right? A Bernoulli distribution has this parameter theta, right? A Gaussian distribution has the mean and the variance, right? Any other distribution has its own parameters, right? So you're going to think about that distribution. You do not specify the parameters. The parameters are unknown to you. And what you assume the samples that you have seen are coming from the true distribution, right? Now, the task that you have, the learning algorithm here, is that you look at the data and you try to find out what are these unknowns, right? The right choice of those unknowns. Everybody's clear? Questions? OK, let's consider binary examples. So let's say that I am collecting a bunch of samples here, right? They're all coming from 0 and 1. What I assume that they are independently coming to me, right? For instance, I would say, OK, every day I go to this game machine. It's just, I'm going to win or lose. They're not changing this one every time I start from scratch. So it seems to be independent samples coming from a random process. And that random process is binary. So what I'm going to do, I'm going to say that, well, every single sample that I see is coming from this Bernoulli distribution with parameter theta, right? So theta is the chance of winning, and 1 minus theta is obviously the chance of losing, right? And every single sample that I see, each time that I win or lose, I'm sampling from this distribution. Everybody's cool? So this is one case. Now, if I want to know, say I have played n times, right? And I want to know what is the chance that I win, say, or if I play n times and I want to see like that specific profile that I have got, like I have win 4 times and I have lost most of the other times. So I want to know what is the chance of this. I would say, OK, this, if I assume it is independent, is just simply the product of all individual probabilities, right? And then it would be basically theta to power number of times that I win, 1 minus theta to the power of number of times I lose, right? So this is the probability of your specific observation when you assume that distribution for your process. Everybody's clear? Questions? So if this is clear, what is the parameter here? What is the unknown? What is the thing that you can easily play with? Theta, right? Theta is something that you don't know, right? Now you want to look at your data and you want to say that what is theta, right? Now before I just proceed with this one, let's say that you play 10 times, you win 4 times, you lose 6 times. What is theta then? You don't need to do anything. Just give me a rough intuitive answer. 0.4, right? You say 4 out of 10 I have won, right? What are the odds? Like 40%, right? Everybody's clear? Okay. So you're going to see that if you do maximum likelihood, you again end up with 0.4, right? And you're not doing something weird in maximum likelihood. Basically, you are just formulating the way that you feel. Now, another example, well, I might have generated some numbers. The example of the heights I told you, I have collected a bunch of numbers. And then I would say, okay, I assume it's coming from a Gaussian distribution. So I assume people on this planet, from beginning of time to the end of time, and maybe if there are some aliens in other planets, some creatures, they have also height, all of them together are independent samples, every single of them, and they are all coming from a Gaussian distribution, right? There is an average to that Gaussian distribution. Most of creatures are around that. There is a variance, which is specifying how this height is spread, right? And then I'm just going to model it like this. So the density for one particular sample that I took of the height is a normal distribution with mean mu and variance sigma squared, right? Everybody's cool? Now, if I see n different people with n different heights, right, I can compute the odds, the density of seeing such n samples together, right? I would say it's the same distribution computed at the height of the first person times same density at height of the second person, so on towards the end, right? Everybody's clear? Questions? Yeah.
In the second line, it says that once it's generated independently, we know that the distribution is Gaussian, but we're actually assuming that it's Gaussian.
We are assuming, right, right. Where is saying that we know?
So the second.
Oh yeah, I mean by know is like either you know really or you assume that. I'm sorry. Yeah, maybe it's better that we assume samples are coming. Yes. Everybody's cool? Again, in this guy, in this expression here, what are the unknowns? What are the things that you can change? Yeah, go ahead. Mu and sigma, right? Mean and variance, they are the parameters that you can change, right? And you want to find the right one. Now again, without thinking about any math, if you want to know what is the average, what do? What is that value of mu? How do you, can you give me an estimate of that? Sample mean, you just look at all the heights that you have inside your data set, you average them out, you would say that's probably a good estimate of mu, right? And again, you're going to see that when we do maximum likelihood, we end up with the same estimation of mu. Okay? Everybody's cool? Questions? No question? Okay, great. So this is the distribution. I just wanted to give you a bit of feeling. I mean, I guess you probably have it very clearly. So say this solid curve is the normal distribution with mu and variance sigma squared. If I reduce the mean value, I'm going to shift it backward. If I increase it, I'm going to shift it forward. If I change sigma, if I reduce sigma, I'm going to somehow concentrate everything around mu, right? So this is going to be something like this. This is getting higher density at the mu, right? And it's going to just drop faster, right? But if I increase sigma, then I'm going to spread my data on a larger interval, right? So I'm going to get into this guy. So this is going to get less density at mu, and then the data is more spread around mu, right? Because the variance is larger, obviously. Right? Okay. Now, let's define something that we call it likelihood. So let's say that we have this particular model. So we assume that the samples are coming from this distribution p theta. And now I'm looking at one particular data set. So in my data set, I have x1 to xn, right? What I can do, I can assume that these samples, for example, coming from independent distributions, right? Sorry, they are generated independently. They are IID. And then I can compute this probability distribution, right? What is the distribution? What is the density or what is the probability of x1, x2, and xn happening all together, right? Exactly the thing we computed in the previous slides, right? I can compute that. If you compute this one, this is what we call it the likelihood of theta. You see? Likelihood of theta. It's not likelihood of your data. Your data has probability of happening, right? It does not have likelihood. Likelihood is the function of your unknown, right? So this is the likelihood of theta. What does it mean? It means that, well, in the example of the Gaussian one, you told me that, well, if I want to choose the mean value, mu, I'm going to average the samples that I have, right? This means that you give a higher likelihood for that choice of mu, right? It's less likely that mu is something far away from that value. Or for example, in the Bernoulli case, you told me that if I just win 4 out of 10, then the best estimate you would give me for theta is 0.4, right? So it means that you are computing likelihood for different choices of theta. Theta could be anything between 0 and 1, right? And then the one which you think is the best one is the one when you set theta equal by 0.4. Everybody's cool? You see what I'm talking about? So likelihood is not computed at a data, right? A data sample. It's computed at a choice of unknown, right? Theta. It is the likelihood of your parameters. Everybody's clear, right? So this is what we call it likelihood. So the likelihood is a function of theta. This is very important for you to pay attention to. And I do know, I mean, some of you might have had some courses on these like statistical inference, and then you have some feeling about likelihood. But if this is the first time, many people have this feeling that, okay, what is the difference between likelihood and probability, right? And these are two different things. Mathematically, if you take integral of a probability on its argument, probability distribution, it's going to be 1, right? For likelihood, there's no reason for that to be 1, right? This is a simple way of seeing the difference. But you need to think a bit more about this. Just try a couple of samples so that you get a bit of feeling about likelihood, right? But right now, what you mean that I set my unknown to be theta. Now I want to see what is the chance of this data set happening, right? That is what you compute as a likelihood. Everybody's cool, right? OK. Now, let's just do it for the binary example. So for the binary example, I have these outcomes, 1, 1, 0, 1, 0. So I have 3 wins, 2 losses. And now I want to compute the likelihood. Can you tell me what is the likelihood here? First of all, likelihood is a function of unknown, right? Theta. And what it would be? Theta to power, how many times you win? 3 times 1 minus theta to power 2, right? This is going to be a likelihood. It's a function of theta. It's going to change as you change theta, but it's not a distribution of theta, right? So how can I compute it? I could say that, well, I assume every single sample is coming from a Bernoulli theta distribution. Now, if I want to compute the likelihood of this parameter on the specific data set given to me, I'm going to compute it this way. So I'm going to say that this is the probability of this outcome happening when the parameter is theta, and this is going to be this guy, right? Theta to power 3, I have 3 ones. 1 minus theta to power 2 because I have 2 zeros, right? That is a function of theta. This is the likelihood of theta. Everybody's cool? Probability of getting that data, so when you specify parameter to be theta, right? Yes, but it's not a probability on theta, right?
It's not the probability.
Data is fixed, right?
Yes.
When you change theta, you're just changing the probability that you are computing, right?
Yes.
You see that? Okay, that is likelihood. This is different from probability, right? When you compute probability, you fix theta, you compute the probability, right? You change x, right? And when x changes, the probability changes, right? Something could happen with high probability, something happens with less probability, right? But when you are fixing your data and you're changing your theta, what you're doing, you see, this is the data that I see. Now I want to see how well my assumption is fitting to that, so I'm going to compute that probability for the given theta. And if I change theta, that value goes up and down, right? But it's only just changing the likelihood. Do you see what I'm talking?
We change the theta, that's why we change the likelihood.
Right, exactly.
And the other way, we change x.
And then we're changing probability, right? Right. Questions? Yeah. Sorry? Yeah, we're going to see next. So we're going to maximize it to find the best density. That is maximum likelihood. Yeah.
Just to continue what was mentioned, so for likelihood, we basically look at the x's and try to see.
Yes, you're right, right. So you look at x's. This has happened, right? Your original process has some distribution you don't know, right? You just assume one distribution with parameter theta. Now you would say that what is the likelihood if theta is this? What is the likelihood if theta is that, right? And you can compare that, right? Yes?
Can you please clarify again what's the definition of the density of data set?
Density of the data set is what you assume, right? Density or probability, right? Yes. For example, here, this is your data set, right? And your data set is a binary data set. Like everything inside, you know, it's either 1 or 0, right? Then you are going to model it. You would say, okay, it's a Bernoulli random variable with the chance of being 1 equals to theta, right? So this is your model. Clear? And now, given that you consider this model, you want to see what kind of what value for the probability this model is going to give you, right? Now, this is what you define as the likelihood. Questions? Yes?
So basically, you're kind of doing like an inverse process where you're
Right.
finding
Right.
the parameter from your data set.
Exactly.
Can you consider the likelihood like a probability density function of your data?
It's the probability of your data, that's correct, given that your parameter is theta. That's correct. Yeah, so it's a reverse inference problem, that inverse inference problem. That's correct.
So because the theta could be between like 0 and 1,
Right?
the total probability that it is that particular value, if you sum over all of the cases, then it should also be 1. So can it be considered like a probability?
You don't need to really assume any distribution for theta if that's what you mean. You don't need. Theta is just unknown. It's a parameter, right? It could be a value. You don't need to think about that theta to be anything specific, like any distribution, right? Here, because of your model, you know that theta is between 0 and 1. That's correct. But maybe like in Gaussian case, mu could be anything, right? And you don't really need to assume any distribution for that. You can assume distribution. I don't want to confuse you right now. We're not doing that. That is the Bayesian inference. That is another story. Yeah? But right now, we're not doing that. Okay? So for us, theta is just unknown, one deterministic parameter that we don't know, and we want to find a good estimate of that. Yeah? Questions? So everybody's cool with likelihood? So let's go. So again, likelihood is only a function of unknown theta. That's very important to pay attention to. I do know it's computed out of probability at the end of the day, but when you think a bit deeper into it, you see the difference. Now, another case is that I have a Gaussian distribution, right? And the Gaussian distribution, I just sampled from that 3 different samples, right? The Gaussian generator, I pressed it like 3 times, and then I got 3 different samples. These are the values I got out of it. And now I can assume that these guys are coming from one Gaussian distribution with mean mu and variance sigma, right? And then I can put it inside that expression and compute what is the density of these three things happening together, right? Which is basically the chance of 0.3 happening, the density of 0.3, times density at minus 1.5, times density as minus 0.1, right? And when you compute everything here, at the end of the day, you're going to end up with only mu, right? And sigma. There's nothing else there, right? Again, this is the likelihood of your mu and sigma choice, right? The mean and variance choice, standard deviation choice, right? So if I change mu and sigma, I'm going to change this guy. That is the likelihood. It's a function of mu and sigma, right? Everybody's cool? Questions? Yep.
How do we interpret the value of likelihood if it's not necessarily bounded to anything?
I mean, if it's a probability, then the sample, the value that you get, I mean, here is density, but in the other example, this should be somewhere between 0 and 1, right? It's computed out of a probability function, right? It cannot get more than 1. The key point is that when you change theta, like if you have two choices for theta, and you do know what is the likelihood at one of them, you cannot talk about the likelihood at the other one, right? There's no reason that that is 1 minus this one, right? I just mean that, right? Clear? Yeah. Everybody's cool? Now, if you got the idea of this likelihood, now the whole learning algorithm that we have, which is a very general learning algorithm and is applied on everything, this is what we call it maximum likelihood, right? And what is the maximum likelihood idea? Say you want to find out what is theta, right? So you don't know what is the best choice of theta in your Bernoulli, so you want to see what is the best estimate you can give for it. Well, if you consider that Bernoulli distribution, you can compute a likelihood, right? And if you change that theta inside that likelihood, you're going to change the value of the likelihood, right? What would be the best choice that you're going to take for that? You're going to take the one which gives you the maximum likelihood, right? And you can think different ways about that. Now, the best choice that you can do, first of all, let's define it mathematically. The best choice of theta, that unknown theta that you can choose, is the one which is maximizing the likelihood, right? So it means that it's maximizing the joint distribution of all those samples you have already seen. Okay? Now, why is that the case? Well, there are a bunch of reasons that you can give for it. The most intuitive reason for that is that, well, let's say I have one random generator and it's just generating samples, right? How many times I can sample it? 10, 100, 1,000, 1 billion times? Well, this is probably nothing as compared to the all possible outcomes that it can give me, right? Correct? So if that is the case, then what are the things that I'm going to see at the end? They are the things that are very likely to happen, right? Because those things that are very unlikely to happen, I never have time to see them, right? Correct? If you just randomly go outside and take one person, right? There are a bunch of diseases on this universe which maybe 1 out of trillion people could just get it, right? Some unknown autoimmune disease, right? If you just randomly select one person outside, it's very hard to happen that that guy has that disease, right? This is something like very rare, right? You need to go and just get into the specific clinic where they are giving service to these people, and then you can meet them, right? But probably if you just go randomly outside and sample random people, it's very hard that this happen, right? Everybody's clear? So the thing that you're going to see randomly is usually the likely things, right? Like, what is the chance of an alien exist? It's not 0, definitely, right? But if you go outside and just randomly knock on someone, is it an alien? Well, no, right? This is not going to happen. Maybe if you just age for a couple of trillion years, then at some point the aliens come to us and then you randomly sample one of them. But this is not likely to happen, right? So the thing that you see, the people that you meet in the street, they are usually typical with typical properties, right? And those rare things happen very hardly. If you want them to happen, you need to sample a lot, right? You need to be a medical doctor who is visiting patients every day, and then you're sampling so many people that finally you see someone with that rare condition, right? So this is one way that you can think about it. So the outcomes that we're seeing, the samples that we're seeing all the time, they are usually the most likely outcomes, right? So this is intuitive illustration, but there is also a mathematical description, which I put it here in the footnote. If you are interested, you can go and do a bit of research on that. So moral of the story, or long story short, if you do maximum likelihood, essentially you are making the KL divergence is a kind of distance measure in the probability domain between the distribution that you are assuming and the true distribution of your data. You are minimizing that. And it makes sense, right? So you want your model to get as close as possible to the original distribution, right? This is why maximum likelihood makes sense. But I don't expect you to see this immediately. You can do a bit of research. The proof is not that hard. And then you can see this as well. Everybody's cool? Questions? No question? So just a few minutes, and then we're going to have a break. So optimal choice of unknown is to just maximize this likelihood, right? So you computed the likelihood at your particular unknown using the data set that you have, and now you play with this theta to maximize this likelihood. So it means that you are going to play with theta to maximize this probability term, right? Now, if we assume that the samples are coming IID, almost all the time we assume that. If we don't assume that, we can do no machine learning, right? So anything that you do in practice is always assuming that. And if you assume that, then it basically means that you get a different probability of every single sample just getting multiplied together. And this is the term that you want to maximize, right? Everybody's cool? Questions? So if you want to maximize this one, well, you can try doing this, but working with such a product term is quite a hard thing in practice. So what we do, we just use the log trick, right? If you have one function, and you do know that this function cannot be negative, right? If you want to maximize this function, you can, instead of maximizing it, you can maximize its log, right? It's the same thing. Log is an increasing function. It's defined on the positive inputs, right? So you can maximize that one. This is the same thing, right? So if you do this, instead of maximizing that term above, you can maximize the logarithm of that, right? And when you take the logarithm of a product, it's going to be sum of logarithms, right? So this is what you're going to compute at the end of the day, right? What is this Ln theta? This is your p theta, the distribution that you assume, and one particular sample xn, right? So you put xn inside, and then this is going to be the likelihood of theta at that particular point, n, right? xn computed, right? And then you take the logarithm, you add all of them up, and then you maximize log of the likelihood, right? Everybody's clear? Questions?